Part E. So we have the limit as x approaches 0 from the right of x plus pi over x all raised to the pi x. So if we attempted direct substitution here, this would give us 0. This would give us pi over 0, and any constant over a 0 is interpreted as some form of infinity. And then pi times 0 would give us 0. So this is actually an indeterminate form of infinity raised to the 0 power. Now remember, an indeterminate form means you cannot determine the result in this form. That doesn't mean you default to does not exist. So this is actually called an indeterminate power. And the problem we have here is that we have something indeterminate happening in both the base and the exponent at the same time. And the only tool in math that we have that allows us to separate an exponent from its own base is natural log. So we're actually going to use that property to help us evaluate this limit. So my approach to this is to make this a little easier is I say, well, let's let this limit be some unknown value L. Now what this does for me is it creates two sides to an equation. So any algebra moves that I'm making, and then my ultimate goal is to figure out what this L is. So I'm going to take the natural log of both sides. So the natural log of L, and as we saw throughout the semester, if you take the natural log of this limit, you're actually allowed to move the natural log inside to the function itself. So the limit as x approaches 0 from the right of the natural log of x plus pi over x raised to the pi x. Now the whole purpose of taking the natural log was so that we can take advantage of the algebraic property it has that says you can bring an exponent down to the front. So this is going to give us the limit as x approaches 0 from the right of pi times x times the natural log of x plus pi over x. So now that I've done this, I want to try to attempt direct substitution again. Now this is no longer going to be infinity, and that's because if we look at this, the natural log here is going to be 0. Actually, this might be infinity, sorry. The natural log here, if we plug in 0 for x, we get 0. We're still going to get pi over 0, which is going to go to positive infinity. So at the natural log of positive infinity, if we know what the graph of natural log looks like, as x approaches infinity, the natural log also approaches infinity. We're still getting 0 times pi, which is 0. So this is an indeterminate form of 0 times infinity. Now, this is called an indeterminate product. So meaning we cannot determine the result in this form. So the strategy that we employ in this situation is that if we move one of these terms into the denominator, now we do that legally, move it into the denominator. If we move the 0 term, it will create a infinity over infinity situation, hopefully. And if we move the infinity term in, it will create a 0 over 0 situation. And the goal here is to invoke L'Hopital. In this particular situation, I would advise leaving the natural log where it is. It's just probably not going to make things better to move that into the denominator, and it can become quite messy. So I would move the term that is not natural log. So the way that we do that is when you move something into the denominator, we have to invoke its reciprocal. Now with trig identities, it's nice because all 6 of them have their own reciprocal identity. But in the general case, we do it the following way. So we're leaving natural log in the numerator, and when I move pi over x into the denominator, it has to become 1 over pi x. And so we can see that if we want to check ourselves, we have this divided by a fraction. If we multiplied by the reciprocal of that fraction, we would come right back to where we started. Now, if we were to attempt direct substitution, we have an indeterminate form of infinity over infinity, and that's awesome because that now allows us to use L'Hopital. So the derivative of the numerator, this is ln of u, so the derivative is going to be u prime over u. And so the derivative of this is going to be 1 minus pi over x squared divided by x plus pi over x. The derivative of the denominator is going to be negative 1 over pi x squared. So rather than putting another fraction down here, I'm going to multiply times the reciprocal. And so negative 1 over pi x squared becomes negative pi x squared over 1 when we flip it. So now I'm going to clean this up a bit and see what happens. So the first thing I'm going to do is I'm going to distribute this across the numerator. Okay, so all I did was multiply this fraction across this. In my denominator here, I'm going to get a common denominator so that I can combine this into one fraction. So that's going to give me x squared plus pi all divided by x. And then I have this divided by a fraction. So I'm going to multiply by its reciprocal. So I have negative x squared plus pi squared times x over x squared plus pi. And now when I try direct substitution, I'll get 0 plus pi squared times 0 over pi. And that equals 0. Now don't forget that all of this work just told us what the natural log of L is. So this means the natural log of L is equal to 0. We still need to solve for L itself. So we do that by raising each side over e, and we can conclude that L equals 1.